Good morning. Tried to forget to record, but all right. So mixed feelings. Last day today. Today is our last class. But also kind of happy. Isn't this such a weird emoji? It's like he's happy, but he's sad. Mixed emotions. You guys have worked really hard, and I'm really proud of you guys. And we've got one final push just to wrap up regression today. I'm going to focus on the things that you need for the final. So there was a little bit more that I wanted to get through, but let's just focus on what you need for the final. And then if you take Stat 240, probably with me next year, then we'll do more regression and we'll kind of pick up where we're leaving off. So if you weren't going to do Stat 240, then maybe it might be fun, right? It's got a data science emphasis, but it applies to just a continuation of Stat 230. Okay, so for review, we started regression, right? And regression is when we have a scatter plot, typically between some x and y, where we have the explanatory variable here, explanatory variable, and the response variable. And we talked about, okay, we can describe this relationship, and really what we're going to get to is we're going to fit this line of best fit, right? So this line of best fit is now going to be called a least squares regression line. And I know that's a lot of words, and it makes it sound fancier than it actually is. It is just a line of best fit, but we're going to call it a least squares regression line. Oh, I should capitalize consistently. Okay. Now the least squares regression line, and I'm kind of skipping through how it's fit, but really what it does is it minimizes the distances and a little bit more, but it essentially minimizes the distances between the points and the line, right? So that's how we arrive at this line. Okay. And so what we say is we're minimizes the distance. The distances, oh, and my computer, of course, is still trying to mess me up here. That's okay. Minimizes the distances between the points and the line, which makes sense, right? Between the points and the line. Okay. Really what we're doing is we're minimizing those residuals, and that's where we ended last day, right? And so we're really, what we're doing is we're minimizing the residuals, E subscript I. So even though we call them the residuals or the errors, right? Errors makes more sense for the E, but I like the term residuals because it makes me think, okay, residual means left over, right? So it's the distance left over between the line and the points. So the residuals slash errors, oops, is going to be the observed y minus the predicted y, which we said was going to be denoted by E subscript I, And really all we're saying is the subscript I is for each point, right? Each point will have a residual, right? Some distance from the line. So in notation, right, we're going to have some EI or E subscript I, and then we're going to have YI, which is your observed Y, minus your predicted Y, which we said had a hat on it, right? And that's kind of where we got to last day. We talked about how do we describe this relationship, right? But I'll leave that from last day. Okay, so we can calculate these residuals. We're not going to. I think I make you do it on the assignment that I posted. So you'll get a chance to try it, but we're doing kind of an accelerated version today. So buckle up. Oops. There. Okay. So the least squares regression line, or the equation for the least squares regression line, is this. The equation for the least squares regression line is y hat, okay, because that is the line, right? The line is those predicted values for every value of x, okay? And so y hat equals b naught plus b1x. Remember an equation of a straight line, y equals mx plus b, right? You might remember that from, I don't know, some other math course. That's the general equation of a straight line. Okay, so if you recall, y equals mx plus b, right? It has the same layout, except we wrote our addition slightly different, right? But whatever is attached to the x is the slope, and whatever's on its own is the y-intercept, right? So in this case, we have b naught, right? So we're going to use b's, and that's okay. We could have used a's and b's or whatever letter we wanted to, but it's because later on in statistics, we use betas for the parameters. And then, so then b's are the natural choice here. But so b naught and b1. So the b1 is attached to the x, and that makes it the slope. Okay, so here, this is the slope because it's attached to the x. B naught, oops, I drew over the naught, is the y-intercept, right? And it's on its own. Y hat is the predicted value of y, and how we're going to use this ultimately is we're going to construct this least squares regression line, and then we're going to predict a value of y for some value of x. So we leave x kind of open for business, and then we can plug in any value of x to find the predicted value of y. Okay. So if I go to that formula sheet that I posted, because that might be nice. Oh, looks like I wrote on it. That's oopsies. What we're going to have, and I am going to kind of go through this quite quickly because I'll show you what you'll need for the final exam. So you will need these formulas for the assignment, and it's good to work through these. And of course, the textbook works through these for you, and also the notes that I posted. But I want to focus on what you need for the final, because I want you to feel comfortable. Okay, so on that formula sheet, right, I've given you the least squares regression line. Is this y hat equal to b naught plus b1x? Okay. And I even tell you that the slope is b1, right? So there's lots of clues on here, even if you don't write this exact one out, right? Make sure that you've got these straight, right? So the slope is b1 and b naught is your intercept. And then we're going to talk about how we find these, but first, for any regression question, you're going to be given 5 pieces of information. Okay, and there's so much information, or it feels like a lot of information, because we're going to have information for X and information from Y. Okay, in fact, we're going to have the mean and the standard deviations of X as well as Y, and then we're also going to have the correlation. Now, let me just make sure that we did talk about we did talk a lot about correlation already. Phew. I forgot that we had, so I had a little panicky moment thinking I had to introduce correlation as well. It's for me to worry about. No. Okay. But what I want to say is for any, started on a new page, for any regression type question, regression type question, and I feel like we even talked about how to calculate it, right? I give you the covariance, maybe I didn't. That's okay, we don't need it. For any regression type question, we will be given 5 pieces of information. Okay, we're going to be given X bar, the standard deviation of X. Okay, so this is the mean of X, or the sample mean of X. Which is really the explanatory variable, right? And then the sample standard deviation of X, and I'm just going to write SD. Y bar is the sample mean of Y. And SY is the sample standard deviation of Y. Okay, so notice here's some X information. And here's the Y information. It's really important that you spend time at the beginning of the question and you figure out what your X and what your Y is, because in your calculations, if you do something silly like 1/2 when it should really be 2/1, right? 1/2 is 1/2 and 2/1 is 2. So you can see how big of a difference you get. And so you don't want to do something kind of weird like that. Okay, but we said 5 pieces of information, and the final piece of the information is the correlation. Okay, and it might be given to you in different ways. Okay, and I'm just going to grab it just in case I didn't last day. The correlation can be found a couple of ways. Okay. I would say just ignore the SXY. SXY is the covariance. Okay. And so I'm not going to scratch it out forever, but that was symbolic. Scratch it out. So you could work through this and you could find SXY, which is the covariance. Right? Or really, what you could do is you could use this calculation for the correlation, which is the covariance over SXXY, which is the standard deviation of X times the standard deviation of Y. So there's a couple of different ways, and the reason I'm skipping through it is because, yeah, you'll need to do it for the assignment. Okay, so you'll use this, or potentially finding the covariance. I can't remember, but you'll use these formulas on the assignment, but it gives you the summations, so that's kind of nice. So you just plug them in. It's not bad. Use this on the assignment. But on the final, R is given, right? So you don't need to calculate it. It's just going to be given to you. Okay. So, so you will have practice on the assignment, but not to worry if it feels hard, or you're thinking, oh man, I'll never have time to work through all these problems. That's okay. You'll be given it for the final. Okay. All right. So what we're going to be able to do is we're going to be able to find the slope. Okay, and the reason we find the slope first is because we actually use it in calculating our y-intercept, right? So given these pieces of information, right, we can find the slope. Okay. To construct the least squares regression line, we first calculate the slope. Even though it's B1, which seems weird, right? But that's just how we have to do it. So B1 is the correlation times SY over SX. And I'm going to just confirm. Yeah. So it's the correlation, which is given, times the standard deviation of Y, which is also given, divided by the standard deviation of X. So this is where it becomes really, really important that you're not doing 1/2 when you should be doing 2/1, for example. All right. So then we use B1 to solve for B0. B0, I think, is Y bar. Let me just confirm here. Working off the cuff. Yeah, Y bar minus B1 X bar. Okay, so Y bar is the mean of the Y's, X bar is the mean of the X's, and of course, B1 is the value from before, right? And then we can put those values in for, then plug those values into the equation. Okay. So Y hat is B0 plus B1X. Okay. These two, B1 and B0, they are replaced by numbers. Replaced by numbers. One thing that trips people up is X is just held as an X. It's we can plug in any value of X and we can solve for the predicted value of Y. Okay, and so that's the beauty of it, is we're going to have this equation that lets us predict a future value of Y. This is left as X. So that we can enter any value of X, I should say, to solve for Y hat. Oops. So the goal is to be able to predict values of y. Okay. So another way, and this is how it's going to be on the final exam, another way that it could happen is using software. Okay, so sometimes I'm going to say often in real life. I almost wrote IRL. Sometimes or often in real life, because you're not going to do these calculations by hand. That's crazy. We will be given software output. We will be given software output. To help us construct the line. Okay. And like I said, this is how it's going to be on the final, is I give you some output and that lets you construct the line. Because I don't want you to, with so little time spent on this in class, I don't want to set you guys up for using the wrong values, for example. Okay. So I said you might be given it, but usually you're going to generate the software output. We haven't really been using R this term, and that's because this course doesn't really have room for all that. So then we start getting deeper in that in 240, but that's okay. We'll know the basics. All right. So we've got a regression question, I see, because I have a scatter plot, and right away I can tell you that because the percent in poverty is my X, what I'm going to do, instead of talking about these percent in poverty and it looks like annual murders per million, I'm going to call it murders, just as shorthand. So when I say murders, I actually mean annual murders per million. And when I say, so my X, I'm going to call it just poverty. But really what I mean is percent in poverty, right? So I'm going to use these kind of shorthand to make it a little bit cleaner. So the graph tells me which is my X and which is my Y. Okay, and the first part that we're going to do is we're going to write out the linear model. Now this looks like a lot, okay, but for our purposes here, all we're really interested in is these first two columns. Okay. So that's all that you need to look at here. And I think you could probably even figure it out without me even telling you what's going on here, right? Because we said we have an intercept, okay? So it says intercept here, and it is the intercept, right? And so this is the estimate for the intercept. And then we have the poverty percent, which is our X. Right, so that means that our slope here is 2.559. Now I'm going to grab this little snippet here. Copy. We're going to blow it up. Okay. So here, this is the y-intercept, which is B naught. Okay. This here is your X. What's attached to your X? Your slope. So that's going to be B1. So what can we do to construct this line? Well, if we want to construct, write out the linear model, so part A, well, the linear model in general, I haven't been calling it that. I've been calling it the longer name, the least squares regression line, but it is a linear model. is B0 plus B1x in general, right? But then we said, okay, we're going to replace these B's with numbers. And that's exactly what we're going to do to write out the model. So then we get y hat is negative 29.901 plus 2.559 times x. Okay. So now that we have the slope, whether we've calculated it or it's from output, then we can use it to predict values. So what I'm going to do is I'm going to add a little, we are going to interpret the intercept. We are going to interpret the slope and interpret the R squared, which we don't know what it is yet. That's okay. We'll get there. But first I want to use this model to predict a value of X. So predict Y, right? We're always predicting Y. Predict the annual murders per million for a state with 22% poverty. Okay. Predict, the annual murders per million for a state with 22% in poverty. Okay. So I always make you use your line to do a prediction. So what can we do? Now, percentages we know are a little bit tricky, right? Because sometimes we have to convert percentages into decimals, right? 22% is 0.22. But here, because the units are in percent, right? So percent in poverty, the X that I'm going to put in is 22. Okay, so that's confusing. And of course, it's not going to be that way on the final, but I just wanted you to see this scenario where, okay, sometimes the units have to be accounted for. Okay, and so what are we doing? Well, we can draw a line, but let's assume that this line with an intercept of negative 29 and a slope of 2.559, let's assume that it looks something like this. Okay. So what are we doing? What am I asking you to do? I'm asking you to go here, and maybe I should make that a little bit nicer looking. Go here and tell me what this y hat is. Okay. So you're not going to do that by eye. That's crazy. I just drew this line on randomly. And even if we're really good at drawing a line, that's great, but that's still not going to work. So we're going to use the equation, of course. Oops. Oh, my page is doing that weird thing where it doesn't want to bounce back. All right. So then y hat, and maybe what I should do is you could write murders hat is negative 29.901 plus 2.559. You do not want to round any of these values, right? They've already rounded, giving you those 3 decimal places. So you don't want to do any rounding. Right? So the predicted murders is negative 29 something plus 2.5 something times the poverty. Right? So you could use this wordy one if you wanted to, right? But I'm just going to stick to the y hat. Y hat is negative 29.901 plus 2.559 times 22. Here, I will make a note, match the units on the scatter plot. Okay. Order of operations. This gets at people every time, I know it. Okay, we do have to do this multiplication first before we can add to this negative number, which is the same as subtracting it away, but let's just do it properly. So y hat is negative 29.901 plus, I need to grab my calculator. $2.559 times 22 puts me at 56.298. Then I can subtract 29.901 and I get y hat is 26.397. Now, what I always do to check my math is 26.397. Does that seem, I know it's crooked here, but it's okay. Does that seem like a reasonable value to get? Yes, it does, right? And so if you're checking against your own graph, for example, right, then you want to make sure that it makes sense, that what you're saying makes sense. And in this case, 29, I mean, I drew it crooked, so 29 does look good, better than my line even. Yeah. And so that's how we're going to use the line. So one thing that I want to highlight before we go on to interpretations, which are important, is this line is built on x's between roughly 14 to 26%. Okay? There's no data that we've used beyond those points, right? So we're going to talk about the range of our data, and unlike typical math scenarios, the range is the y-axis, but now we're going to talk about the range of our x's. Okay. And so here, right, this is where we built it. So this data is what built this line. The problem with the line is it does go from negative infinity to positive infinity, right? It just keeps going and going and going and going. And it keeps going and going and going and going. So we could use this line for predictions outside of these values of x. Okay. So what I'm talking about is something called extrapolation. And if you look at the notes, I have some pretty fun examples of extrapolation gone wrong, right? And sometimes it's intuitive, like growth. So if we talk about growth of children, for example, then we know that between the ages of I don't know, probably 2 to 12 for sure, right? We've got this very strong linear relationship. But then, you know, you keep growing, but maybe not as much. And then eventually we stop growing, right? And so we know that. So if we use this line between the ages of 2 and 12 to predict our heights when we're 50, that's going to be way off, right? Unfortunately, we don't always have that gut feeling of, whoa, that doesn't make sense, right? And so it's easy to kind of get trapped in extrapolating, but that is my next thing. Extrapolation. When we use the line, the linear model, to predict using values outside the range of our data, and we use values of x in our linear model, that are, I'm going to say, far outside. So we do have a little bit of wiggle room, but if we move too far away, so far outside the range of our data, okay, so that's extrapolation. And usually it's one of those words that people forget on the final exam, and they'll write stuff like, oh, no, it's bad because of that word that I can't remember, and that's fine. You guys are open books, so you'll remember, but just in general, I think it's pretty cute. It's like, no, there's a word for it. I can't remember it, but I remember the idea, and that's all I care about. And so that's when we use values of X in our linear model that are outside the range of our data. Now, the tricky part is that's still our best guess, but it's not a reliable guess. Okay. An extrapolated prediction, is likely still our best guess, right? Unless we have a different model that we should be using, but usually that's not the case. Okay, so an extrapolated prediction is usually our best guess, right? But it's not a reliable guess. Okay, so it is the best thing that we have, but it's not a reliable guess because we're extrapolating. Is usually our best guess, but it is not a reliable estimate / prediction. So then, for example, right, what if I added a part here? So I did part I for AI, A double I. So here we go, part double I. Now I'm going to make you extrapolate. We're still going to do it, but there's a little note that we add at the end. Okay. And so here, right, the range of our X's go between 14 to 26. So we have a little bit of wiggle room on either side, right? Maybe we just didn't see those data points. But if we go to 50% in poverty, for example, that's not going to be a reliable guess, but it is our best guess. Okay. And so now if I say, predict the annual murders per million for a state with 50% in poverty, predict the annual murders per million for a state with 50% in poverty. And then I usually kind of prompt you by saying something like, do you trust this prediction? Okay. So my X is going to be 50. And so I can still use my line, of course. Y hat is negative 29.901 plus 2.559 times, and I'm just going to plug it in here, 50. I have to do my 2.559 times 50 minus 29.901. Make sure you do proper order of operations here. I get 98.049. Okay. Do I trust this prediction? My answer here is going to be no, right? No, because 50% in poverty is an extrapolation. No, I do not trust this prediction. That's not enough, right? You don't get any marks for saying that yes or no. You have to tell me why. Why do you not trust this prediction? Because we're extrapolating beyond the range of the data. No, I do not trust this prediction because we are extrapolating beyond the range of the data. Good. Okay. So what's really important is once we have our output, right, we need to be able to use it to make predictions. That was the whole goal here. But also, especially if you are if you're generating this information or this model for a client, for example, then you need to explain what these values are. What do they mean? Okay. And so what we do is we take the definition of the slope, we take the definition of the intercept, and we apply it to these to this specific problem. Now, in the beginning, and this is where we kind of get to in this course, it's not going to sound that good, right? But it will be technically correct, so no one can fault you. Okay, so there's a kind of a weird sentence structure because all we are going to do, so we're going to take that definition and we're going to apply it to this scenario. Yeah. So the interpret the slope. Okay. And notice how that's kind of the meat and potatoes of this problem, right? Is okay, write out the linear model. That's good. That's arguably quite easy, right? Especially if you have the output, you can just plug things in. And then most of the work here is interpret the intercept, interpret the slope, interpret R-squared, which I'm going to introduce by definition. So we'll get there. Yeah. So let's see here. I'll make this part B. Interpret the slope. Okay, so the general definition of the slope, and I'm gonna, the slope. The slope is the predicted value of y when x is 0. No, it's not. That's the intercept. I'm on autopilot. Sorry. Interpret the slope. The slope, oh my gosh. The slope is the increase in the predicted value of y. I was so close. The slope is the increase in the predicted value of y for each unit increase in x. There we go. For each unit increase in x. A unit is just one increase in x. So for example, if x is the percent in poverty, it's a 1% increase in x, right? So just 1 unit. Okay, so if you look at your equation, so in general, right, you've got y hat is b0 plus b1x. If you stare at this long enough, this definition will come out at you, right? And so if you say, okay, the intercept is just steady, right? That doesn't change. So then if x goes from 1 to 2, right, then you can find the predicted value of y when x is 1, okay? Write that down, and then you can find the predicted value when x is 2, and what you're going to find is that predicted value of y has increased by the slope amount. Now, the slope can be negative, of course, if we have a negative relationship, but I just always say increase, right? And so the values that we're going to replace here, the slope, we're going to replace with a number. Okay, so this is where it doesn't sound that good, right? But in our case, right, 2.559 is the increase in the predicted value of y, and of course we have a y, and let's call it murders, for each unit increase in x. Replace these with values from the question. So if you're asked to interpret the slope here, right? Interpret the slope. 2.559 is the increase. And so just as a heads up, right, if you have negative 2.559, right, you can have a negative slope, but then if you say negative 2.559 is the decrease, that's not right, right? So if you always say increase, then you're always safe. Okay, so I always say increase, even though it sounds weird, but a negative 2.559 increase is a decrease, whereas a negative 2.559 decrease is an increase. So you don't want to contradict yourself. So I always say increase, even if it sounds weird. So 2.559, in our case, we have a positive slope, so we're fine. 2.559 is the increase in the predicted value of annual murders per million. For each unit increase in percent in poverty. So see how I've just replaced these values with the appropriate thing from the question. So you take that general definition, which I've given you, right? So you're going to have it handy somewhere, right? And then you take that general definition, and then you tweak it to match the question that we're working on. Okay. So for you, because you will have access to all your notes and the textbook and all that fun stuff, then it's just a matter of taking that definition and applying it to the question. Okay. Same thing with interpreting the intercept. Now, ultimately, our goal would be that you actually remember these and you have these, right, kind of in your vocabulary, but so that's something to work towards. But for now, let's just focus on the final exam. All right. C, interpret the intercept. It's understood that it's the y-intercept, so usually we don't even say it. If we think about our equation again, B naught is our intercept, right? And so how do we get our intercept? Well, if I let x be 0, then this chunk goes away, and then the intercept is the predicted value of y when x is 0, right? So again, if you stare at this long enough, the definitions will shine through, right? But we're just gonna blow right past that. Intercept. The intercept is the predicted value of y, and this is the one I started saying earlier. The intercept is the predicted value of y when X is 0. And we do the same thing again, right? So I'm going to highlight which portions we swap out. The intercept is, of course, a number, in our case, negative 29.901, I think. And that is the predicted value of Y, which is actually the annual murders per million, when X, which in this case is the percent in poverty, is 0. Okay. So in this case, negative 29.901, I'm pretty sure, let me confirm. Yeah. Negative 29.901 is the predicted annual murders per million when the percent in poverty, is 0. Okay, so it sounds a little funny again, but right, I'm just trying to give you the easiest way that you can answer these questions and still be technically correct. That's really important, right? Is that we're saying things that are technically correct. So the intercept is a number, negative 29.901, is the predicted annual murders, and maybe I'll say value of annual murders if we want, annual murders per million, when the percent in poverty, which is X, is 0. Usually what I do is I follow this up with, is this meaningful? Okay, so a line, because it keeps going from negative infinity to positive infinity, at some point it will cross the y-axis, right? It has to. So, but sometimes that's useful information and sometimes it's just an anchor, right? It's just where it crosses the y-axis. It doesn't mean anything. And how we get to the bottom of that is, can X be 0, right? At the y-axis, X is 0, right? And so that's the definition of the y-intercept, right? And so really what I'm asking is, can X be 0, right? Is that a reasonable value for X? Okay. One of the things we could check is we could check the original scatter plot if we have it, and we could say, it doesn't really look like a 0% in poverty happens, right? The lowest we have here is 14-ish. And so 0 would be way out here. Keep going, keep going. I guess these are steps of 4, that's weird. Anyways, so it would be somewhere way out here, right? And so really what we're doing for the intercept now is we're extrapolating, right? And so that's not meaningful, right? It's just where this line crosses the y-axis. So here I'm going to add my follow-up question that says, part I, is the intercept meaningful? Really what I'm asking is, can X be 0 reasonably? Can X be 0 reasonably? Okay. So in this case, I would argue no, but this is one of those things where you pick a camp and you stick with it, right? So if you tell me that, yes, it's meaningful because there might be a state someday with 0% in poverty, then we would predict negative murders per million. Not reasonable to me, right? But if you tell me that, yep, that can happen, and that's useful information, then I'm fine with that, right? But your argument has to be centered around, can X be 0? So in this case, because X equals 0 is extrapolating, that's my reason for saying, no, it's not meaningful, right? And so we have to argue if X can be 0 reasonably. Okay. Since X equal to 0 is an extrapolation, the y-intercept is not meaningful in this case. There are times when X equals 0 is a perfectly reasonable outcome. So if we think about temperature, right? So degrees Celsius in Kelowna, for example, well, then we're going from, I don't know, -25 to way beyond 30, right? And so we cross 0 at some point, and that's a perfectly reasonable temperature to have recorded. And so then the intercept is meaningful, right? It's just a benchmark of, okay, when the temperature is 0, then we see this in Y, right? We predict this to happen in Y, right? And so your argument has to be centered around X being 0. Can it be 0 or can it not be 0? Okay, so it's another one of those where if you tell me yes or no without any information, I can't give you any marks, right? And you have to center it on, can X be 0? And you argue it either way. Okay? So as long as you argue it either way, I'm happy, I'll give you the mark, but it has to be based around X being 0. Okay. So just like we did, we introduced those general definitions of the slope and the intercept. I'm going to do the same thing for the R-squared. Now, if you've done any sort of regression in the past, fit a line of best fit, you've probably also generated the R-squared, right? And the reason for that is because R-squared is a metric that we use to tell us how good our line is. How good is this model? How much has this model captured? So this was C. So now I've got a fresh page here. It doesn't look like it, but I do. Interpret R-squared. Now I'm going to grab it from here. And there are a couple of different options here. Oh, let it catch up. We're given R-squared, but also R-squared adjusted for only one value of X. And spoiler alert, we can have 2 values of X, and I make you practice that on the assignment, but you do exactly what we've been doing here. And I'm going to let you fly on your own for that one, because we're going to do this on the final. But for in general, we can just use this R-squared. Okay. So here, I'm just going to copy this so we can have it down here. Paste image. Okay. Interpret R-squared, it said. Okay. R-squared, the definition of R-squared, a lot of highlighting on here. R-squared is the percentage of variability, okay, or the proportion, right? Percentage and proportion are the same. One's the decimal version and one's the times 100 version, but R-squared is the percentage or proportion of variability in Y explained by the least squares regression line on X. That's really wordy, right? But let's write it down. So a variability in Y explained by the least squares regression line on X. So our goal today is just to start to recognize, okay, as soon as you see percentage or proportion of variability, so something of a variability, right? Alarm bells start going off in your head, right? As soon as you see this wording, right, think R squared. Okay, so because it becomes this wordy definition, right? R squared is the percentage of variability in Y explained by the least squares regression line on X. But as soon as you hear percentage of variability, your mind goes R squared, right? Oh, that's R squared, right? Whether you're asked to calculate the R squared, which I'll show you how, or if you have it given, right, then it might say, what is the percentage of variability in Y explained by the least squares regression line on X, right? So just recognize that sentence structure and then think R squared, okay? So in this case, R squared, how can we calculate it? So it's a capital R. R squared is something weird happens, is the correlation squared. So it is the correlation squared. So we need to be able to work kind of back and forth here, but if you have the correlation and you're asked to find the R squared, then you need to square your correlation. And then if you want it as a percentage, you have to multiply it by 100. If you want it as a proportion, then you leave it as is. Okay. So kind of options. Option 1 is you're given the correlation and asked to find R squared. All right, then you just take your correlation squared is your R squared, right? And then multiply by 100. Multiply by 100%. If percentage is needed. If percentage is needed, right? Because that'll be a proportion and that's totally fine. The other way that we could ask this question is, okay, well, what if you don't have the correlation? What if you have, what if I've given you the R squared like I have here, 70.52, or I have, the textbook has here, right? How can I find the correlation? Well, we'll be given R squared and asked to find the correlation. So R squared is the correlation squared. So first thing we need to do is we need to, R squared has to be converted to a proportion. Convert to a proportion. Okay. Once you've done that, you've got a value for R squared and you're trying to solve for R. So you can take the square root of both sides. The square root of R squared, but when we take the square root, we have to reattach the positive and the negative, or whichever one applies, right? And there's tricks to doing that, but that's going to be your R. Okay. So here, R will be positive if the relationship is positive. Remember, the correlation is the strength and the direction of a linear relationship. So you make it positive if you have a positive relationship. And you can get that from the slope, right? If the slope is positive, then you have a positive relationship, which we do in this case. Or if you have the graph, then you can look and say, okay, if I have a positive relationship here, then I need a positive correlation. So R will be positive if the relationship is positive. Slope is positive, and or scatter plot is positive. Whereas R will be negative, and I should say positive. If the relationship is negative, of course. Right, negative slope, or the scatter plot is negative. Slope and or scatter plot. Sometimes you're not given the scatter plot, so that's why I'm saying and or. Scatter plot is negative. Then you have to do that little bit of extra work to add on the negative onto the correlation. Okay. So then, interpreting the R squared, in this case, I kind of got away from that, right? In this case, R squared, which is 70.52%, is the percentage or proportion of variability. So 70.52% of the variability in annual murders per million explained by the least squares regression line on percent in poverty. Interpret R squared. 70.52% is the percentage of variability in annual murders per million explained by the least squares regression line on percent in poverty. Nice. Right? So we're swapping out R squared for a number, and we're swapping out Y, and we're swapping out X, just like before. Okay. And then finally, I think we're going to calculate the correlation, which we already know how to do from that definition. Calculate the correlation coefficient, which is just the correlation R. Okay, so let's see here. DE. Calculate the correlation coefficient. I get lazy and I don't call it the correlation coefficient. I just call it the correlation, but that is R. All right. So we were told that R squared is 70.52%. So R squared as a number is 0.7052, or as a proportion. So then I'm going to take my R squared and set it equal to my correlation squared. I can replace this R squared with 0.7052 is R squared. I take the plus minus square root of 0.7052 is the correlation. Square root of 0.7052 is 0.839761871, which is our correlation. And it's going to be positive, since the relationship is positive. Since the relationship and slope, of course, are positive. So it's positive 0.839. Good. Good. Okay. So let's see here. Last thing I wanted to do. There's a lot of other things about, and of course, so what we talked about today, I do talk about in way more detail in the notes. Okay. And so if you find it helpful to kind of flip through these notes, then that's great, right? We talk a little bit more about Rsquared and all that fun stuff. And then let's see here. I have my last thing I want to do is just copy this. So that's kind of it for what we call simple regression. Multiple regression. Now I'm only introducing this so you can tackle that one question on the assignment where I'm pushing the limits here. It really just means multiple explanatory variables. Okay, so it's going to look something like this. But as long as you kind of keep your cool, you'll be able to construct this least squares regression line. Okay, and I always find it a little bit more helpful if I can write it out with the names of the variables. Okay, and so I think in this one we're predicting the GPA, and we're going to construct this model. So Y is GPA, and study week is what we'll call X1, sleep night is X2, out night is X3, and X4 is the gender, which is what we call a binary variable. It's going to be 0 if it's female in this case, and a 1 if it's male. Okay. So what we can do is we can say Y hat is, so what you do is you take your intercept from here, and then you've got all your coefficients that you attach onto your X1, X2, X3, X4. So a lot of variables. 3.45 plus 0.00 times X1, that seems to go away, right? 0. Plus 0.01 times X2 plus 0.05 times X3 plus negative 0.08 times X4. Okay. Or the predicted GPA is 3.45 plus 0 times the study week plus 0.01 times the sleep night plus 0.05 times the out night. And then I'm going to do minus 0.08 gender. Now I can't remember what so study week the number of hours they study at night, the number of nights they go out, and their gender. Sleep night, out night, I don't know what all these are. But what you can do is if I give you values for x1, x2, x3, x4, just like we did with just one x, right? If I asked you to predict the y for when x was 22, for example, you just plug that in and you do the same thing here. So it would say something like, predict the GPA for a student, well, study week, this is going to go to 0, so I don't really know what that is, but who sleeps for 8 hours a night and goes out 2 nights in a week and is female, right? Predict the GPA for a student who sleeps 8 hours a night. I know, wishful thinking, right? Goes out twice per week. And is female. The GPA, the predicted GPA is going to be 3.45 plus 0 plus 0.01 times 8 plus 0.05 times 2 minus 0.08 times 0. And with my last breath here, 0.01 times 8 plus 0.05 times 2. The other ones go to 0 plus 3.45. I'm getting a predicted GPA. Pretty good, 3.63. There, you did it. And I'm so proud of you guys for hanging in there. Hopefully you find regression as fun as I do. It's not as heavy as the other stuff that we've covered, but we've covered a lot of ground. Thank you for this term. And I hope that all your final exams go well and that you have a great summer. All right. If you have any questions, let me know, but I'm going to stop this recording. See ya.